All right, today we're going to do a mix of laboratory and calculations. So this one's going to be looking at equilibrium constants today. I talked about ways to determine K. What were the ways to determine K? The actual numerical value of K. Yeah, look it up in a table or measure it or calculations. Calculations we did was the KP and KC, but there are additional calculations for that. And so what we're going to do is we're going to do both. We're going to look it up in a table, and we're also going to measure. And so let's take a look at some equilibrium that we can. So the first one we're going to look at is ammonium chloride. When you think of ammonium chloride, what are the chemical properties of ammonium chloride? Well, one thing is, most ionic compounds are solids when pure. Can you think of any ionic compounds that is metal and non-metal or salts that are liquids or gases? Maybe sodium fluoride. What would you guess? Sodium fluoride, liquid, solid, or gas? Sodium fluoride? Well, HF would be a gas. Hydrogen fluoride would be a gas. Yeah, but that's more hydrogen fluoride we call a molecular compound. Ionic compounds have these lattices of ions. Cation and anion, simple array called. So this would be molecular. This would be a gas here. But any salts, what is a salt? Usually a salt is an ionic compound that's not an acid. It's salt. So can you think of any salts that are liquids or gases? Yeah, I can't either. So all of them are solids, basically. So, when we have these, but some of these are soluble, some are not. How about this one? Do you think this was soluble or not soluble? This is soluble. And so what we end up with is ammonium chloride, aqueous. Now, ammonium chloride aqueous, is that a strong electrolyte, weak electrolyte, or non-electrolyte? It's a strong electrolyte. Soluble salts are strong electrolytes. What else are strong electrolytes? Strong acids are strong electrolytes. Weak acids are weak electrolytes. What else? Strong acids and strong bases. Yeah. So soluble salts, the strong electrolytes are the soluble salts, the strong acids, and the strong bases. And we know that strong electrolytes do what? They dissociate completely. So this is going to consist of ammonium ions and chloride ions. And then we look at the chemical properties. What are the chemical properties of ammonium? Well, one thing is it's an ion, so we probably should look at metathesis properties. So what other ions does ammonium precipitate with or react to form a gas? Something like that with. Well, maybe just think about what ions will ammonium precipitate with. Well, you go back to the solubility rule. Solubility rule says the group 1 and ammonium salts are all soluble, so nothing. So metathesis is pretty unreactive. Right? You can react with anything. We go to acid base. Ammonium is what? Ammonium has a base. Ammonium, though, is not a base because if ammonium is a base, then it has to be a proton acceptor for Bronsted. And then what would form is NH5 2 plus. And then you try to draw the Lewis structure for NH5. So we'll put a nitrogen in the middle and then 5 hydrogens. This, but there's a problem because I need 2, 4, 6, 8, 10 electrons to bond that. But if I look at N has 5 valence electrons, and then I have 5 hydrogens. And that would be 5 valence electrons, but I have a +2 charge, +2, -2 electrons, so that gives us 8 electrons. Well, I can't. I have to remove one of these, just have this hanging out here, and then call this. Does that Lewis structure look good to you? No. And so NH4 plus cannot be a base. It doesn't have the capability to violate enough electrons. Then it would violate. If it did have enough electrons, it would violate the octet law in this case, which is nitrogen. Ammonium cannot be a base, but it could be a acid. In fact, there's no problem with ammonium losing a hydrogen. Ammonium loses a hydrogen in what form? Yeah, NH3 and H plus. But is ammonium a strong acid? No, ammonium is a weak acid. Weak acids only partially ionize or partially hydrolyze or partially dissociate. And so in reality, this is favored in the reverse direction. It's favored in the reverse direction because we're going from a weaker acid to a stronger acid. This is uphill. But in Chem1B, we don't do dissociations like this. In Chem1B, we're going to do what's called hydrolysis. Hydrolysis means if we're interested in what it is in water, then what we're going to do is do this. We're going to say ammonium is our acid, water is our base. What forms from this? Yeah, H3O plus and NH3. Okay, we know it's a weak acid. It's a weak acid, meaning it only partially dissociates. In fact, which way is the downhill direction, we suspect, for this reaction? Is it downhill to the left or is it downhill to the right? Well, what we do is we look, okay, going forward, ammonium's the acid. Water's our base. Going backward, which one loses the hydrogen? Does hydronium lose the hydrogen or ammonium lose the hydrogen? So let's say if ammonium lost the hydrogen, it should form NH2 over here. And so we will start off with NH3, we go to NH4, so ammonium gained the hydrogen and the hydronium lost it. And so the species that donates the hydrogen is the acid, and this is the base. And then we compare, which one's a stronger acid, hydronium or ammonium? Hydronium is stronger, this is weaker. And which is a stronger base, ammonia or water? Ammonia. This is weaker. And so the weaker side is more stable energetically, and so it's downhill backward. And so what's happening here is this: it's not too steep uphill. That is, could be some forward uphill reaction here, making it partially partially. What we call this is partially hydrolyzed. Hydrolysis is like breaking apart water, but whenever we have a reaction with water and the water changes, then we call that hydrolysis. Okay, so this is the way we say this is ammonium partially hydrolyzes water to form hydronium and ammonia. Now, what we want to know is how much, Can we talk about percentage? Well, the problem with talking about percent hydrolysis, which we do, talk about percent of it, 1%, 10%, 50%. When someone says there's partial hydrolysis, how much? But we want to know what the percentage is. But we can't use percent hydrolysis to tell us, or predict, because let's say I got 1% hydrolysis. Is it going to be 1% hydrolysis for everything? With ammonium, no. It changes depending on what we start off with. And so, what we want to do is we want to figure out what K is, for one thing. What is K? And so, let's take a look at the reaction. Our acid base chart. Well, let's make a prediction, just a rough prediction. If we have a rough qualitative idea, it's always nice. So ammonium, what do you rank it as far as acid strength goes? Pretty weak. And then water is a pretty weak base. And so the reaction here is ammonium and water. That's pretty steep climb, right? Pretty long climb for this. Because then we're going to form hydronium. Hydronium is a much stronger acid than ammonium. That's way uphill. And we're also going to form ammonia, which is a much stronger base than water, since we're inverted. So this is a very steep uphill climb. Will it make it? Yeah, it's a weak acid, so a little bit should make it, but how much will make it? Well, that's what we're going to try to find out, how much makes it. And what we're going to do, I expect K to be what do you expect K to be? Kind of big or pretty small? You expect it to be pretty small because, that's such a steep uphill climb. There's probably very, very few in the population that can make it up there. And so we'll try to figure it out. And so what we can do is we can try to figure this out experimentally. That's what we're going to do today. Well, only K is probably a good. We'll talk about how to copy finite, this kind of stuff. But for right now, we're going to look at K. So we're going to do determining K by measurement of equilibrium concentration. If I have a beaker, and this beaker is labeled 0.1 molar ammonium chloride, what this is the what we call the initial concentration. Because that's, it's like weighing out 0.1 moles of ammonium chloride salt and then dumping it into water. So if I take some of this ammonium chloride, the pure salt, weigh out 0.1 moles, I need the mole now, and then mix it with water, then that's what's going to give me a 0.1 molar solution. But we know that ammonium is a weak acid, and so what that means is a little bit of the ammonium from that salt I just dissolved in there will hydrolyze water to form a little bit of ammonia and hydronium. And so what's going to happen is, how much of this are we going to lose? You know, are we going to lose 10% of this ammonium? Because if 10% of the ammonium, then that's going to result in, the hydronium and ammonia here. But I don't know how much. And so what I'm going to do is I'm going to set up, this is the way we set up Chem1B problem. Your book doesn't always do this because, once you know this pretty well, you take shortcuts, but I usually don't take shortcuts. I set up everything using an ice table. We'll get to chloride later, but let's just concentrate on ammonium right now. Okay, so initially I mix up this solution with 0.1 moles per liter. And so I start off with 0.1. Now, is it okay to use moles in this? Or do I have to use molarity? What does the pattern show? Well, I have to use molarity. Even though using molarity is a bit of a pain sometimes, you get used to it. You could use moles here. So for example, if I had a liter, I'd call it 0.1 moles. I could use moles, but the problem with that is at the end, I'd have to reconvert everything back into molarity. This is an extra step I don't want to do. So I'm just going to use 0.1 mole. Now, does the molarity of pure water change? No. So pure water, what we do is we just draw lines through it. It's a pure liquid. It doesn't change. And when I mix this up, when I take that salt and dissolve it in the water, do we have any hydronium or ammonia at the start? And the answer is no, because I just mixed it. And then as soon as I mix it, then the ammonium can react with the water to form this. There's going to be a change, but I have no idea how much it's going to change. And then I need this. I need to know what the equilibrium concentration of ammonium is. How much did I lose? If I lost 10%, then I'm at 0.09. If I lost 20% of this, then I'm at 0.08. And so what I need is the equilibrium concentration of ammonium. And I need the equilibrium concentration of hydronium. And I need the equilibrium concentration of ammonia. And so I got to figure out a way to measure these. And so how am I going to measure this here? Out of these three, which one do you think will be the easiest to measure? Concentration of. Which one? Yeah, maybe the ammonia or the ammonium. I don't. Yeah, liquid. You know what? I don't write aqueous. If there's nothing written there, it's aqueous. If there's something written there, then it's liquid, solid, gas. I did write aqueous over here just to emphasize. Well, let me tell you which one's going to be the easiest. Measuring the ammonia is going to be difficult. Because it's not a really easy way of doing that. And the same thing with ammonia. Do you waft the vapors to your nose and then smell how much ammonia there is and then determine it that way? Yeah, you could. I mean, if your nose was well calibrated, that would be pretty impressive. I had a friend, when I was at UCLA, I had a friend that was working at the Hyperion water treatment plant here. And he told me his boss would go around and stick his finger in the sludge and then taste it a little bit. And then he could tell, he could tell by the taste, certain compositional. I thought that's got to be. But you never know because there are people out there that they work at this for 40 years or something like that. And, they can hear things or they can smell things or they can see things that, normal people can't. But anyway, so I don't know. These are going to be hard, but it turns out measuring the hydronium concentration at equilibrium is easy. Very easy to do. And how can we do that? How we can do that is via a pH meter. If we use the pH meter, and let's talk about pH here. You can measure the pH of this solution. So we just stick the pH meter in here, like this, and then measure the pH of the solution. And what the pH tells us, it's going to give us a number. And that number is going to be from, negative to beyond 14. There's going to be a range. And what pH is this is the power, it's a power function. So this is the power of the H plus concentration, or hydronium concentration. Hydronium and H plus we use interchangeably, but in Chem1A, I always use H plus, and Chem1B will always use hydronium. Yeah. And so when I do chemical reactions, I don't want to deal with hydronium. It's the extra step that I have to go out. H plus is not that. And if we take a measurement of the pH, so we just measure it experimentally, and then what we can do is we can calculate how much hydronium is there at equilibrium. So the pH is equal to the negative log of the hydronium concentration at equilibrium. So there are different types of pH meters here. Okay, so why don't you guys can work individually or you can work in together, but you're going to have to check out some equipment from the stockroom. The way you check out equipment from the stockroom is you'll just go over to the window, and then there's a clipboard. You'll just write your name and write your locker number on the clipboard, and they're going to give you a tray of equipment here. And so just grab the tray of equipment, and then going to go through the operation of the pH meter together. So why don't you go ahead and check out the equipment, and then we'll talk about how to do this.